All right, everybody, 10 o'clock. Welcome back to your favorite class. Yes. All right. Announcements. Homework number 4 posted on failure theories, 3 problems. That's going to be due on Monday. Next week, I've already had some questions on it. Number 2 is a bit tricky, so I'd say give it a go and ask me if you have questions. All right. Your first exam will take place next week in the lab period. We've already kind of had a little bit of the buckling lab. We had the lab yesterday. We're still making our way through the buckling notes, but we're still meeting and doing the buckling lab currently. So you have 2 weeks to do the buckling lab. That'll be due not next week, but the week after. And that's because next week, like I said, you have your first exam for this class, which will take place during the lab period. So be aware of that. I'm putting together practice problems now. I should have practice problems posted by the end of the day with solutions. Okay? So take a look at those practice problems maybe over the weekend, really solidify your knowledge. All right? One other announcement I have to make here is that there will be no in-person lecture on Friday. Okay, I've got to make a little bit of a family emergency trip to Pittsburgh, and I have to leave Friday morning. So no in-person lecture, but I will record a video and post it, and you guys can watch the lecture like we would normally have. You can watch it at the normal time if you want to stay consistent, but no in-person lecture on Friday. Okay, so I'm going to record a video probably today and post it for the next portion of the lecture. So that's that. All right. I'll also send out an email about that to remind you guys, and so nobody shows up on Friday by accident. So those of you that normally come on Friday in person, I'm sorry. It's a personal thing I gotta attend to here. So no one's in trouble. It's something I have to take care of. Okay. So right. Any questions right now? A little bit more formal announcement about the exam coming in email probably today as well. Joe, you're here and here. He's in 2 places at once. He's like the Flash. All right, cool. Well, let's pick up where we left off then. And we were in the middle of our derivation of critical buckling load in the buckling notes. So let's pick it up where we left off here. Not that. I want this. Okay. Also, for those of you that handed in your lab report yesterday, I'm like 75% of the way through. I think most of you have gotten it back at this point, but there's a couple that's still outstanding. So I try to stick to the 24-hour rule, but I didn't quite make it this time. Okay. Sorry. I got sleepy last night. Okay. So let's talk about where we were. We were deriving the critical buckling load, and these are the notes that we had going last time. And the basic idea is that you have some long, slender member here that's going to be loaded. Whoa. Some long, slender member. Let's come back here. Some long, slender member. Jeez, stupid thing. That's going to be loaded axially. So we have these loads P that are kind of being loaded at the end of this structure, sort of this pinned configuration. And that is causing this bar to sort of be bent with this sort of curvature that you see here. Right? So the idea here is that we're going to label the neutral axis of this bar that's sort of in bending with this elastic curve, this v of x, and that sort of tells us the amount of deflection that we have off of what would be the normal x-axis. Okay. And from this, we know that there are internal forces and moments through the bar which we cut, and that allows us to write an internal moment that is occurring at that particular location in terms of the applied loads, and it looks something like this, where that moment is the negative load times v of x, where v of x is the distance that we've displaced from the buckling. Right. That's our general sort of setup here, and we're going to go through the governing differential equation of beam bending to sort of derive what is this critical buckling load that would cause this to occur. So that's kind of where we were last time. And the next step would have been to look at this general governing differential equation for bending, which is like v double prime equals m over ei, something you should have seen in 2004. And we were kind of making our way through that. All right. So we did that, put it in sort of standard form, as you sort of see here. And then we assigned this p over ei to be omega squared. So here we're making a substitution. for omega is square root of p on I. And that gives us this differential equation for the bending situation that we currently have right now. And this is the equation in your differential equations class. Hopefully you talked about this very standard equation. This is an equation for a simple harmonic oscillator. If not in your differential equations class, hopefully you talked about it in your not vibrations. What's the class? Oh, gosh, dynamic systems. Is that it? Yeah, dynamic systems. All right. Gosh, vibrations and dynamic systems to me, like, they're equivalent. Okay, but anyway, so there's your governing differential equation for a simple harmonic oscillator. And if we want to quote unquote solve this particular equation, we need boundary conditions and a general solution. So we said that the general solution for this particular governing differential equation, v of x, is given by a sine omega x plus b cosine omega x. And like tweaking out behind me. And then the second derivative of that particular equation looks something like this. And so if you were to plug these two pieces of the general solution back into the governing differential equation, which is up here, you would satisfy this particular governing differential equations for all values of a and b. All right, that's kind of what it means to be a general solution for a differential equation. Now, to more accurately solve this general equation, we need boundary conditions to find capital A and capital B. And so we were talking about some of the general boundary conditions for this particular beam and bending. And sort of bending, but it's actually buckling. And some of those boundary conditions are identified by like the pinned configuration that we have. So we have like a pin on the bottom here, pin on the top here, and that allows us to define some things about, let's say, the displacement at those pins, which would be a boundary condition, and also the bending moment at those pins, which would be 0. So we laid out all of those boundary conditions here, and we're going to use some of those to solve our general solution. We had kind of made our way through that a little bit by using boundary condition number 3, which we said was no bending moment at x equals 0. So that is this particular boundary condition here. And if we plug that into our general solution, just here, and we set that to be true, what you'll find is that the coefficient b is going to be equal to 0. And that was using boundary condition number 3. And that sort of simplifies our general solution down to this particular form. And now we have to look at, all right, one more boundary condition so that we can solve for this variable capital A. So that's about where we left off last time. And we're getting a little bit mathy, but it's all going to hit a practical point very soon. So I know it's kind of been it was a mathy day last time. I hope you brought your math pants and were wearing your math pants. But we're going to put it to a head here and actually show what it means in reality moving forward now. Okay. So we've used boundary condition number 3. Now let's use we'll use boundary condition number 4. And to remind you what that is that the second derivative at x equal L is equal to 0. Okay, so if we work this guy down, and we want to take the second derivative of that, this is just going to be negative a omega squared sine omega x. And we'll insert our new boundary condition here. Okay. So if I do that, my left-hand side here is 0. And we have negative a omega squared times sine of omega times capital L, which is the length of the bar. They're plugging in L for x. Okay, so the question then is, what values of A make this true? Okay, so someone give me one value of A that might make this true. Jordan says 0. Okay, cool. I agree with that. We say one trivial solution is capital A equals 0. That doesn't really tell us anything. It just says that if we have no load on the bar, that our boundary conditions are met, which is obvious. Okay, So this doesn't really tell us any information. The other more interesting condition would be if this portion of the equation were generally equal to 0. Okay? So the non-trivial bit is the solution sine of omega L equal to 0. This is the interesting portion for us. Okay? And I'll show you why that is here in just a second. So if this is kind of the important bit of information, then I'll ask what values make this true for, let's say, omega L, right? How would this be satisfied? What value does omega L need to be for this to be true?
0.
0 or some integer of pi, right? So 0, pi, 2 pi, 3 pi, etc. So to satisfy, omega L has to equal plus or minus n times pi, where n equals -1, 0, 1, 2, ... Okay, integer values. This is like the important bit, and this is how we sort of derive the critical buckling load, right? We enforce the governing differential equation must hold given certain boundary conditions, and we look at the non-trivial solution, which here would enforce that this omega L has to be equal to n times pi, right? So remember what omega L is. So we'll enforce omega L equals n pi. And recall that omega is, we defined this before, square root of p on EI. Right? Hopefully it's all coming together. So let's plug this back in. And see what value of P makes this true. All right. So we would have something like square root of P on EI times L equals n pi. We rearrange for P. You will have n squared pi squared EI over L squared. This is your critical buckling load for failure. Okay. Where n equals 0, 1, 2, 3, etc. Integer values. All right. Now, what does this really represent? What is the n squared? All right. Well, let's talk about this. And what is n physically? Well, if we plug in n equal to 1, this would get you back to what you would have seen in your 2004 class. That particular equation. All right. The picture here would look something like this. If you're applying load on the ends, this is kind of the picture you want to have in your head. That would give you something that looked like this for your bar. It's buckling, and it's buckling in the fashion that you're used to seeing, okay? This is the smallest possible load that could be induced to cause buckling. Right? And remember, this is like V of x, right? And we have a general solution for V of x. Uh-oh, did I just lose the call? No, okay, I'm still on the call. Made some funny noise. Okay. You could go through a similar process and look at what happens if n is 2. Here we have n squared pi squared, so this is going to be 4 pi squared EI over L squared. The picture here, we still have the same bar, but if we use a value of 2 for n, we have a different equation for v of x that we could draw that might look something like this. Okay. And you could sort of continue with this process. Okay. So recall, we had this general solution that was Vx equals, like this A sine omega L, right? Where omega contains your p-value, okay? And so basically we're just changing the frequency of what the shape of the beam looks like with different values of the critical load satisfying the governing differential equation. So what you see here is that, all right, if I put this amount of load on my structure, then I'm going to see bending in this particular fashion, or I'm going to see buckling in this particular fashion. This is the like smallest amount of load that could potentially induce this buckling. And so when you talk in 2004 about like what is the critical buckling load, you just talk about this like first modality that could potentially exist. But there are other modalities that could exist, right? Including higher order modalities, which would be like a situation where n is equal to 2. And that would give you sort of a structure of your piece that looked like that. I don't have my ruler, but usually I bring the ruler and I try to like make this happen and try to like show it. But you can imagine if I had a long slender ruler and I like bent it, I could potentially induce enough load to create this like snake-like structure for the ruler. I mean, you could get these like other modes if you tried hard enough. Okay. Similarly, you could go up to, if you put this much load on the ends, you could induce this sort of behavior inside of the bar, and so on and so on. Okay, so we say that these integer values of n represent the buckling modes. The smallest load to induce buckling is when n is equal to 1, obviously. And we call that the critical buckling load. And you have probably seen this as PCR, pi squared EI over L squared. So this is, again, just deriving something that you should have seen in 2004 already. There's a nice kind of picture of the various buckling modes in the notes if you haven't kind of seen the notes. So go ahead and take a look at that. All right, so we talk about this like critical buckling load, but in this class we like to talk about like a critical buckling stress. Okay, that's just something that's a little bit more useful to discuss, right? Like the load is nice to know what load would cause failure, but most of the time we want to talk about like what stress values would cause failure because we're usually analyzing in terms of stress, not in terms of load. And when we talk about eccentric loading later, we're going to talk about the stress on the cross section, not necessarily the loads. Okay, so we want to speak about what stresses might cause failure as opposed to what loads might cause failure. So let's talk about critical buckling stress. And to do that, I need to introduce a new geometric constant. Which we call the radius of gyration. Usually given by the variable little r. Or the general expression for the radius of gyration is the square root of the area moment of inertia of the cross-section A divided by the cross-section of that particular area A. Okay, so this is the definition of radius of gyration. The units of like meters or feet, length to the 1 power. So remember that this is like length to the 4th, this is like length to the 2nd. So length to the 4th divided by length to the 2nd gets me length to the 2nd. Square root is length to the 1st. Right, so radius, you would think like a typical measurement. So why is this important? All right. Well, it's important because if we talk about failure stress or the critical buckling stress, so critical buckling load and divide by area A. That would give us a critical buckling stress on the left-hand side. Critical buckling load divided by the cross-sectional area. Then you get the critical buckling stress on the left-hand side is pi squared E. I'm going to write this as I divided by A. Because remember, I need to divide both sides by A. All over L squared. Okay, we just introduced the radius of gyration. So this guy here is actually the radius of gyration squared. Actually, it's the inverse of the radius of gyration squared. Nope, it is the radius of gyration squared. So this could be rearranged as pi squared E capital R squared on L squared. Or strangely, it is sometimes written by kind of bringing the radius of gyration into the denominator. So can bring this guy down into the denominator here. And is sometimes written, most commonly written, as pi squared e divided by this term L divided by R squared. This is your critical buckling stress. All right. Oh, baby. Maybe time to define some things. This is the critical buckling stress. E obviously modulus. L is the length of the member or the column. And R is radius of gyration. We just kind of defined what that was above. Here, square root I on A. Okay. Interestingly, this little term in the denominator has a special name. This term here. And we define this value L over R. It's what's known as the slenderness ratio. This gives you an idea of how slender your column is. Okay? It's like this, how long is it versus how large is the cross section, right? So the bigger your cross section, more or less, the larger R is going to be, and the smaller your slenderness ratio is. It's an indication of how resistant your structure is going to be to failing by buckling. Okay? So this slenderness ratio actually is a very important quantity when it comes to determining whether or not your material is going to fail. Now let's consider a situation where we're loading up some rectangular cross section. All right. Let's talk about preferred buckling direction. All right. So let's consider a rectangular cross section. Okay, and I'll just draw it here. Okay. I'll call this side length little b, side length little a. And I'm going to say that there's a coordinate system here on this cross section, sort of at the center. It's like x, y. My question is, if I load this particular column, let's say on an end fashion, this rectangular column, my question is, about which axis will this cross-section buckle? It could potentially buckle sort of about the x-axis, or it could buckle about like the y-axis, right? It could potentially sort of bend about each one of these axes. Nobody has like a ruler on them, do they? I wish I forgot my stupid ruler. Dang. Okay. But the point is that, you know, you're loading up these edges, and you want to know, if I have the cross section of this general shape, is it going to sort of bend about the x-axis, kind of like by the right-hand rule, or is it going to like bend about the y-axis, kind of like by the right-hand rule? And I think it's rather intuitive from just practical standpoint, if you've ever like done this with a ruler, that you know that it's going to bend about, in this instance, like the x-axis, right? So if you sort of like compress this, it would sort of tend to bend around x. But I want to show mathematically why, and I think we have the tools now to sort of show why that is. So let's consider we'll let A be greater than B. Right? Then we can consider the area moments of inertia and the radii of gyration about each one of these individual axes separately. So area moments, handwriting today, of inertia are the following. The area moment of inertia about x is going to be 1/12 AB squared. And the area moment of inertia about y is going to be 1/12 A cubed B. I don't know why I wrote square. This should be cubed. Okay. So if A is greater than B, then obviously IY is greater than IX. I think that's pretty obvious from these kind of equations. And if we recall that the radius of gyration is the square root of I on A, then it's going to be pretty obvious that the radius of gyration y direction is going to be greater than the radius of gyration in x. Because the area doesn't change from situation to situation, the area of the cross-section stays the same. So the radius of gyration in each of these two different directions is this particular relationship. Right? This is useful because this allows us to define slenderness ratio, which allows us to look at what the critical stresses are to cause buckling. So then slenderness ratios remember, a slenderness ratio is like L on R. Going to have the following relationship. What am I putting here? Greater than or less than? If Ry is greater than Rx, what goes in this inequality here? Less than. Right? And now with sigma critical equal pi squared E on your slenderness ratio L on R squared, you'll see that the critical buckling load Y compared to critical buckling load X is going to have what relationship? If this is less than this, yeah, greater. Okay? This is the whole point here. The stress that you have to put on the cross section to buckle it about the y-axis is greater than the stress that you have to put on this cross section to buckle it about the x-axis. Okay, so the point is it will buckle about x-axis first. Okay, and if we sort of go back to our picture, we can sort of envision that. So here's our particular cross section. If I loaded it into the plane, it would want to sort of bend about the x-axis. Okay, so in general, columns spelling is hard. Have you guys ever seen that shirt where it's like, I'm an engineer, I'm an engineer, I'm an engineer, and then like engineer is spelled wrong every single time, and it's like crossed out, crossed out, crossed out, and then it says at the bottom, I'm good at math. That's pretty funny because we're terrible at spelling, but we're good at math, in theory. About axis with smallest slenderness ratio. Smallest? No, largest slenderness ratio. Sorry. The more slender it is, the more likely it is to buckle about that axis. All right, so let's do an example. We'll sort of wrap it up today. Okay, so here's to an example problem. 8-foot long pin-ended timber column. It's going down, milling timber. Has 2 by 4 inch rectangular cross section. Let's determine the slenderness ratio, critical buckling load, and the ratio of axial stress under the action of buckling load to the elastic strength of the material. Ooh, complicated. Ooh, spicy. Reminds me of that Burger King commercial when they had like the spicy chicken sandwich, and some guy would take a bite of it and go, "I'm spicy." This is like 5 years ago. Okay, no one else knows that commercial except me. My fiance laughs at me because sometimes I do that, like for eating Chinese food and it's spicy. I'm spicy. All right, maybe another 15 seconds or so. Okay, let's do it. We have this example. We have the modulus given to us for this particular material, 1.9 MSI. We have that the yield stress of the material, which comes into play in part C of this problem, 6,400 psi. We're told that it has generally a length. This particular column was 8 feet. And we're given dimensions of the cross section. I'm just going to draw the cross section here. And here, this is 2 inch by 4 inch. So here we go, 2 inch by 4 inch. And let's put some coordinate system on this guy to make our life easy. X and Y. All right, we want to find first, what we're looking for in part A is the slenderness ratios. So that would be L over Rx and L over Ry. These are our slenderness ratios about X and Y. In B, we want to determine the critical Eulerian buckling load. So here that's PCR. And in part C, I want the ratio of the yield stress to the critical buckling load. So let's call this, I don't know, capital R, which is the yield stress to the load that would cause buckling. Those are the things that we're looking for. Let's dance. All right. So here we go. Part A. To calculate our slenderness ratios, we need the radius of gyration. We need these radii of gyration. And so let's do this. So Rx is going to be square root of the area of inertia about the x-axis divided by the cross-sectional area of the piece. So here this is going to be something like the area of inertia about the x-axis is going to be 1/12 bh cubed. This will be 1/12 the base, which is 4 inches, times the height, which is 2 inches cubed, all divided by the cross-sectional area of this particular piece, which obviously is 4 inches by 2 inches. Okay. So my radius of gyration about x, if we work this out, 0.58 inches. Similar kind of idea for radius of gyration in y. Iy on a. (1/12 hb cubed). So this will be 2 inches times 4 inches cubed all over my area. 4 times 2 units inches squared. So my radius of gyration about y here is going to be 1.15 inches. Now my slenderness ratio. I don't know, I've been eating a lot of frozen pizzas lately. I think my slenderness ratio is kind of going down these days. Oh, not me, the column. Oh, sorry. So let's do about x first. The total length I'm told is 8 feet. Better not use 8 in this equation. We want 8 times 12 because we're working in inches. All over my radius of gyration in x, which you said is 0.58. This will give me a slenderness ratio about the x-axis. Here it is going to be 166. Similar for y. Except here now we'll use a radius of gyration about the y-axis, 1.15 inches. And this will give me a slenderness ratio about y, which is 83.5. Okay, so my dudes, since it's Wednesday, my dudes, what axis am I going to buckle about? Which axis is more slender? X, right? So the slenderness ratio about x is larger, so we're going to buckle about x. These are the answers for part A. So we'll buckle about x-axis because it's more slender. That particular axis is more slender. It's laid off the frozen pizzas, unlike me. Frozen pizzas and ho-hos. No, actually, I'm a sucker for Flamin' Hot Cheetos. Put that on a frozen pizza. Oh, man. Now we're talking. All right. So we're going to buckle about x-axis. This is important for us to know because when we do the calculation of the critical buckling load, which is sort of part B of this problem, we know our general equation is something like pi squared EI over L squared. And it helps us determine what value of I we're going to use. Okay, since we're buckling about the x-axis, here we need IX. So this is just kind of a plug and chug, so let's just do it. Pi squared, my modulus I was told, 1.9 MSI, multiplied by IX, which is going to be 1/12 BH cubed, which is 1/12 the base, which is 4 inches, times the height cubed, is 2 inches cubed, all over the length of this member squared. Just don't forget to multiply by 12. And you're going to have a critical load for buckling here of 5.43 kips. Okay, it's 5,430 pounds. Okay, baby. Let's roll. On to C. Part C, we're asked for the ratio of the yield stress or the failure stress to the critical buckling load. So remember, we're trying to solve, let's say, capital R for ratio, which is sort of the critical failure stress divided by what would cause buckling, the stress that would cause buckling. So we need the stress that would cause buckling. It's pretty obvious that that's just going to be the load that would cause buckling divided by the cross-sectional area for centric loading. All right, so we know the load that's going to cause failure is 5,430 pounds divided by the cross-sectional area, which is 2 inches times 4 inches. Or the critical stress that would sort of cause failure by buckling is going to be 679 psi. It's sort of an intermediate solution, so I'm giving it a nice box. And finally, this ratio, we're given the yield stress or sort of the failure stress. I guess the timber is not really going to yield, it's just going to sort of fail. This failure stress here, we're given as 6,400 psi in the beginning of the problem, divided by the stress that would cause buckling, which is 679 psi. And we'll get a ratio here that's approximately equal to 9.4. All right, so what does this ratio actually mean physically? Well, that means if you designed your column to fail by the failure stress, you're like 10 times more than what's actually going to fail, okay? So you done messed up, okay? Yeah. Because it's going to fail by buckling 9.4 times lower stress than what you anticipated or what you originally called for in your design. So you can sort of see why it's very important to sort of consider this buckling mode of failure, because you could fail at significantly lower loads and stresses than you might normally anticipate if you were just designing to, let's say, the failure stress of the material. Okay. So that's going to be it today. I will record a video and post it for you guys to watch on Friday during this time. So sorry, no live lecture on Friday, but should be the only time in this quarter I have to do this. All right, thanks for coming, and I will see you on Monday. Unless I have you tomorrow for lab, in which case I will see you tomorrow.